A big part of natural language processing is getting computers to understand language. But before you can do that, you need to get the language on the computer in the first place. We're going to talk about the very basics of how that happens. First things first, computers use binary numbers to store information. That means that each piece of information is either a 0 or a 1, a bit. This is a picture of ancient core memory in a computer, where each of these little magnets have either a positive or negative magnetization. You combine those individual binary digits into a number by multiplying the binary digit by the corresponding power of 2. We'll often use a hexadecimal code as a shorthand because each hex character corresponds to 4 bits. For example, A corresponds to 10 in decimal, which requires an 8 and a 2. If what I'm saying isn't a review for you, I heartily encourage you to check out D is for Digital, which is an excellent resource for going over these concepts from first principles. Okay, let's talk about how bits become characters that you see on your screen. 8 bits, 2 hex digits, is a byte. Back in the old days, when we didn't have all of these fancy fonts and doodads, we had what was called the American Symbolic Code for Information Interchange, or ASCII for short. It maps the integers 0 to 127 to characters. An example, 6541 in hex, is mapped to the capital letter A. You can build an array of these characters to form a string. Note the difference between the A you see on the screen and A, the hex character. But ASCII wasn't enough. We needed more characters. Unicode Transformation Format, UTF for short, is an extension of ASCII that provides representation for most human languages, not always perfectly. But there are so many of them, particularly Chinese characters, that we can't store them in a single byte, so we sometimes need multiple bytes. Because all of the ASCII characters start with a 0, if a byte starts with a 1, that's a sign that we need multiple bytes to encode a character. So you count the number of 1s before you get to a 0, and that's the total number of bytes you need to represent a character. So, for example, Ma, in the Chinese word for Maryland, is E9A0AC, 3 bytes. And sure enough, the binary hex code for E is 1110, so after the byte E9, you have to read 2 more bytes to get the full character. Unicode is a bizarre and beautiful beast. We won't have time to revel in all of its glory, like how you can use zero-width joiners, a non-printing Unicode character, to create new characters compositionally. But let's get back to the main story. We can spell out a word like Maryland as an array of characters. But that's not how we actually want to represent it in a computer. The word Maryland means something. Marylander means something similar, but different. We want to represent those meanings somehow. One way of representing a word is with what's called a one-hot encoding. Map the string Maryland to an integer, and then the vector that represents the word Maryland is a 0 vector except for the index that Maryland corresponds to. An alternate representation is for this to be a dense continuous representation, another vector. We'll talk about both of these representations later, but the bottom line is that both of these need the same first step, an integer map. Because even for the dense representation, that's just looking up the vector for Maryland as a row in a bigger matrix. We'll now talk about how people do this for real in a second, but let's talk about some alternatives. Let's say that you get a string that says this is some text, and you want to turn that into some integers. You could get integers for each of the bytes in the string, but that's not what we want. Those are the characters. We want an integer per word, with all the caveats about what a word is and if words even exist. Why not just split on white space, you might ask? Well, you first end up with problems with punctuation, and this is limiting the discussion to English. Some languages like Chinese, Japanese, Thai, Khmer, Lao, Burmese, and other languages don't use white space to delineate words. Okay, but that's easy enough to fix. Why not just have a regular expression to find our words? This causes problems with contractions and words like C++ and abbreviations, where the punctuation is arguably part of the word. But people were really good at making regular expressions back in the day. Couldn't you craft a better regular expression to deal with all of that? You can, and if you're working with English, the pin tree bank tokenizer works pretty well. We'll talk more about the pin tree bank itself when we discuss syntax. In that case, you also need words to be terminals in your syntactic parse of a sentence. But the thing is, no matter how good you make your rules for finding words, you're not going to catch them all. So you need to set aside a mapping for unknown tokens. This special token is often called OOV, or out of vocabulary. So you need to run through your dataset, count all the tokens you see, and then take the n most frequent as your vocabulary. Call everything else OOV. You don't want to put everything into your vocabulary though, because your downstream models need to know how to generalize. They need to know how to handle an OOV, and otherwise you'd also run into memory. Another problem with this approach is that it doesn't take into account the internal structures of words. Words are made of morphemes, prefixes, suffixes, and so on, and we can take advantage of that structure. Next up, we'll take a look at byte pair encoding as a quick and easy way to represent words and parts of words.
Thanks for watching this video. I picked out another video that you can watch up here. If you want to get more context for the videos, check out this link or the link in the description. It gives you readings, programming assignments, and other things that might be more helpful. Finally, help me out and help other people find this content by providing a big gradient to the recommendation algorithm. Like the video, subscribe, or leave a comment down below with mistakes that I've made, newer research that has come out, or just tell me about where you are in your journey.